Okay, guys, welcome. Today we're going to talk about some trigonometric identities. And essentially what we mean by an identity is some other equivalent form of sort of an existing quantity that we're concerned with, right? So we're sort of looking at some things that are equal in terms of trig identities. So what we're going to do is we'll look at deriving some of the basic trig identities, and we'll use that to simplify some trig expressions. We'll talk about some identities for if you want to look at the opposite of the angle or the clockwise version of the angle that you're currently looking at. We'll also talk about trig identities for 90 degrees or pi over 2 radians minus a particular angle, and then also some trig identities for an angle plus multiples of pi. Okay, so this is something that we've already mentioned, but I just want to sort of stress this again. This is just sort of a notational thing for your trig functions, and the reason why we sort of write it in this way rather than, so this left side is the preferred sort of format for writing these powers of sine, cosine, and tangent. Now, the reason why we don't use this is because you can sometimes, if you don't put the parenthesis there, especially, you can confuse the power to be on the angle. So we don't usually use those forms of powers to of a trig function, right? So we'll usually use the format on the left. Okay, now again, probably the single most important trig identity is that cosine squared plus sine squared is equal to 1. Most of the other trig identities that we'll look at are derived from this fact. So this is definitely one to keep in the back of your head. Now, if you wanted to, you could solve this for either sine or cosine. If you subtract, for example, sine from both sides, you get 1 minus sine squared. And then if you take the square root, you would get that cosine is plus or minus the square root of 1 minus sine squared. Okay. Now you can also do a similar thing if you had just moved the cosine over instead, and you can say that sine of theta is equal to plus or minus the square root of 1 minus cosine squared. And of course, how do you know if it's positive or negative? You would hopefully know what quadrant that your angle was in, right? So that would help to indicate whether you're going to be looking at positive or negative. Okay, so in this first example, we're going to write tangent solely in terms of cosine. Now, we know that tangent is sine over cosine. All right, now this cosine in the bottom, this is okay because we only want our expression that contain cosines, but the sine we want to change to cosines. Right, so if I wanted to solve for an expression in cosine, I know that sine squared plus cosine squared is equal to 1. And I know that on the previous slide, we talked about what the explicit relationship is, but just to show it again, if I want to solve this for sine, I would subtract cosine squared from both sides. I get that sine squared theta is equal to 1 minus cosine squared. So my sine is, again, plus or minus the square root of 1 minus cosine squared. Now, we don't know what quadrant we're in, so we're just going to leave this as plus or minus 1 minus cosine squared, and then over the cosine that we didn't change. Right? So now we have an expression for tangent that's written solely in terms of cosine, right? On one side, we just have cosines. On the other side, we just have tangent, right? So that's one example of how you can use these identities. Now, the next identity that we're going to talk about is that if you do 1 plus tangent squared, that's going to equal secant squared. Now, what you can do in order to derive this is, let's look at cosine squared plus sine squared is equal to 1 again. Well, if you divide everything, so divide each term, by cosine squared. Well, if I divide cosine by cosine squared, that's going to become 1. If I divide sine squared by cosine squared, so we know that sine over cosine is tangent, and then the squareds will make this tangent squared. And 1 divided by cosine squared, of course, we know that secant is 1 over cosine, and the squared will make this a secant squared. So this identity is obtained through the cosine squared plus sine squared is equal to 1 by dividing each term by a cosine. Right, so this is another common identity that we'll frequently use. Okay, so let's look at another example. So we want to simplify the expression where we have tangent squared of theta times this ugly looking fraction thing right here. Okay, now as far as going about simplifying these expressions, usually what we look to do is we want to break this up into something that, of course, looks more simpler, which is sort of the basic idea. But in general, we can work with the complicated one first. So work with the more complicated expression first. Okay, so let's go ahead and do that. Now, of course, the more complicated expression is going to be this one, because I didn't even want to say it when we introduced the problem, right? So what can we do with this thing here? Well, we don't know too many helpful identities for just cosine by itself. If it were 1 minus cosine squared, that would be helpful. But we don't have anything too much if it was just a singular cosine. But what we can do is we can find a common denominator and add these two things together. So this one, I'd want to multiply top and bottom by 1 minus cosine. And this one, I'd want to multiply the top and the bottom by 1 plus cosine. Now, if you multiply the denominator out, here we actually want to multiply it out because we have a difference of 2 squares, and we're going to get something that we want. We're going to get 1 minus cosine squared of theta, right? And in the top, we're going to get 1 plus cosine plus 1 minus cosine. So in the top, these cosines cancel out, and we're just left with a 2. And we know that 1 minus cosine squared from sine squared plus cosine squared equals 1. If you subtract cosine from both sides, we know that 1 minus cosine squared is sine squared. So I can actually put a sine squared here. So this complicated thing in the parentheses eventually became 2 over sine squared. So far, here's what we have. We have tangent squared theta, and we've just transformed that second thing into 2 over sine squared theta. Well, now let's maybe take a look at the other one. Tangent squared, we know, is sine squared over cosine squared. And if we're going to multiply that by 2 over sine squared, we can see that these sines are going to cancel out. And we're left with 2 over cosine squared. And we know that if we have a cosine in the denominator, that that's a secant squared. And that's a pretty nice consolidated expression for the thing that we started with, right? So we could say this is 2 times secant squared. All right, now in general, there's a couple strategies for doing stuff like this, right? So strategies for simplifying. One thing that you can do is what we did here is you can add the fractions. Usually when you find common denominators, good things happen. So we'll say add fractions by finding a common denominator. Another helpful strategy that often helps is convert everything to sine and cosine. Right? And of course, another strategy is to do what we did here, and it's usually to start with most complicated expression. Right? And finally, the last thing is if something doesn't help, try something else. There's not usually one way to do this, right? So if something does not help, try something else. Right? And that last step may seem kind of obvious, but the idea is that there's several ways that you can break this up, right? Like, for example, I may have looked at this tangent squared and thought, okay, well, maybe I could do something with this identity. I could say that that's secant squared minus 1, right? And that could have also led us to the final answer. We don't know that because we haven't done it, but there are several ways that you could go about doing one of these simplifying problems. So just don't feel like there's only one way to do it. Okay, so next we'll talk about some identities involving the negative angle, right? And a lot of these can be found by looking at the unit circle, or at least be sort of seen from the unit circle. Okay, so let's say if we have an angle, we don't know what it is, we'll just say we have an angle right here, right? And if I wanted to go the negative direction, we could say that this is negative the angle. All right, now if I could draw a little better, that's actually not too bad. You can see that these points would give us everything that we need, right? Because this would be cosine and sine of that angle, and this would be cosine of the negative angle and sine of the negative angle. Well, of course, what's the relationship between these? The relationship for the cosine anyway is that these are the same x value, right? So these are equal. And that's what you're seeing here. If you have cosine of the negative angle, that's the same thing as cosine of the positive angle. The x value is not going to change, right? Now, for the y value, what's happening is that you're reflecting it over the positive x-axis. So that's where you're getting the opposite happening, right? So you would need to take a negative there. So the sine of the negative angle, you'd see a negative out front. Now for tangent, you can use the fact that this is sine over cosine. And again, these are each the negative angle. But sine, you know the negative comes out front. And for cosine, you know that that goes away. But this is just negative tangent. All right, so that one's not too hard to see either. All right, now some other angles that are related to if you want to take an angle and subtract, if we want to take 90 degrees and subtract the angle, what happens there? And this is sort of another interesting thing that we can look at here. All right, so let's just look at the first quadrant of the unit circle. Okay, so that's 90 degrees. So this is pi over 2. All right, now let's say that I have an angle of theta here again. So we'll say that's theta, right? Well, if I wanted to get what's pi over 2 minus theta, pi over 2 minus theta is this part. It's the part that's left over. Right? So there's a couple of things that we can sort of look at here that relate to this. Right? If I want the cosine, for example, of this angle here, well, then that's the same. Let's think about this point right here. This point right here is cosine of theta, and it is also sine of theta. Right? So what we can see there is that that's going to be the same point for the pi over 2 minus theta case, right? So it's also going to be only now it's a little bit different, of course, because now your angle, of course, would have to be let me put it this way. Actually, this is probably the better way to look at it. So let's say that I have an angle of theta. Let's put it this way. All right. Well, you know that in a triangle, you need 180 degrees, right? Or you need pi radians, right? So you know that the 90 degrees is pi over 2, or 90 degrees. You have theta. So what's left up here must be the difference between 90 degrees and theta, or pi over 2, right? Now, this side is cosine of theta, but it's also sine of pi over 2 minus theta, right? Because it's also opposite this angle here. Now, this side is sine of theta, but it's also cosine of pi over 2 minus theta, right? So that's where these identities are coming from, right? So you sort of switch the fact that you have sine and cosine there, right? And you can show that the tangent identity is true because instead of y over x, this is now x over y, because the sine and the cosines will switch. And of course, these are the equivalent identities, but instead of radians, we're just looking at degrees. All right, so let's do an example regarding that. So they said show that cosine of theta minus pi over 2 is equal to sine, and that's really what we did, but we can do it again just for fun. Maybe I can explain it a little bit better with a larger triangle. Let's say if we have an angle theta here, all right, and I'm going to call this x for now. Well, we know that 90 degrees, let's use radians since we're using radians here. We know that 90 degrees, which is this thing, plus theta plus x has to equal 180 degrees. All right, and we'll convert this to radians in a second. But what this means is that if I subtract 90 from both sides, I'm going to get that theta plus x is 90 degrees, and then subtract theta from both sides, and I get that x has to be 90 over theta, or in radians, this is pi over 2 minus theta, right? So if I'm looking at the cosine of pi over 2 minus theta, well, the cosine of pi over 2 minus theta is this side. So this is cosine pi over 2 minus theta, because that's the adjacent side. But it's also, since this is theta and this is the opposite side, this is sine of theta, right? So that means that these two things have to be equal, which is what we wanted to show. All right, so that's sort of the idea there. Right? Now, if you think about this from a translational sense, if this is true, this means that the graph of cosine is the graph of sine shifted over by pi over 2. And of course, that's what you're seeing in these two graphs, right? Because on the cosine graph, you have the point 1 comma 0. And on the sine graph, you're getting the point 1, of course, at pi over 2. And everything else is also shifted over accordingly. So this is the same graph, except we've shifted over by pi over 2. Right? So that's an important fact regarding sine and cosine. Okay, let's look at some other properties regarding if we add a multiple of pi. Now, if you look at this on the unit circle, right? Let's say if we have an angle theta again, and we want to talk about, well, what's the relationship between if we add a multiple of pi to this? Well, this is just going to come directly out the other side, right? Now, what's the relationship between these points? Well, this is cosine of theta, sine of theta, and this would be cosine pi plus theta, sine of pi plus theta. All right, well, since these are just coming out the opposite end, both sine and cosine will be the negatives of each other, right? So that's what you're seeing here. This is just coming directly out the opposite end. Now, tangent is going to stay the same because remember that tangent of pi plus theta is sine over cosine of theta plus pi. And both of these just became negative, but negative over negative is positive. So this is equal to tangent. So tangent will retain its sign. Okay. So let's use the result that if sine of pi over 10, this is sort of an interesting application, is square root of 5 minus 1 over 4, right? Now, again, just to be clear here, pi over 10, if we wanted to convert that into degrees, you would find that this is an 18 degrees. All right, so it's not a nice, neat angle. So if you type this into your calculator, you're going to get a gross decimal. But the exact answer is this, which we'll show later on. All right. Now, we're going to use this fact to find sine of 11 pi over 10. Now, if we're careful about this and we write this in another way, we know this is sine of pi plus pi over 10, right? Because if you add pi and pi over 10, you find a common denominator, you're adding 10 pi plus 1 pi, which is 11 pi. So these two are the same thing. But we just said that if we add sine of pi, sine of an angle plus pi, we get the same thing. So this is the same as sine of pi over 10 by the identity that we just talked about. So this, is, of course, is what we just said, or what was given, I should say. This is square root of 5 minus 1 over 4. And that's the sine of 11 pi as well. Or sorry, it's negative this, right? Yeah, it's negative this. Right, because when you add a multiple of pi, you flip the sign for sine and cosine. All right. Now, of course, the identities for 2 pi are easy to see because this is just adding one full rotation. And if you add a full rotation, you're back to where you started from. So there's not really much to show for that. But if you add 2 pi, just keep in mind that your trig functions will stay the same. Right? And these are sort of the extensions if you add multiples of pi. If you add an even integer, you're back to where you started from, because if you had 2 pi or 4 pi or 6 pi, you're just completing multiple rotations. If you add an odd integer, you're going a half rotation, right? Because pi is a half rotation. 3 pi is a half rotation plus another full rotation, right? So the odd integers would produce the half rotation, so you're going to take the negative for sine and cosine, and a full rotation, you would just keep it the same. Now, tangent is the same regardless. Any multiple of pi added to an angle for tangent is going to be the same, because if you add a half rotation or a full rotation to tangent, it's going to stay the same either way. All right, so that concludes this video on trigonometric identities. I hope you enjoyed it, and I will see you next time.